So let's talk about period. We've talked about oscillators making a complete cycle. Sometimes we are interested in how long and what's the time it takes for it to actually complete a cycle. So we're going to present the equation for the period of a mass spring oscillator. We're going to present it in my favorite type of way. We're going to present it without proof. If you're interested in the proof, I am sure you can find it online. Do a quick Google search, but showing you the proof is not going to really help you out much. So the equation for the period of an oscillator is going to be this 2 pi times the square root of m over k. So T is still the period of our oscillator, m is its mass in kilos, k is going to be that spring constant in newtons per meter. So with that, what we can see is that the period is dependent on two things, the mass and the spring constant. If you have a larger mass, the period is going to have to increase. Think about it. Larger mass means it's going to be much more difficult to accelerate. So for it to cover that whole distance of one complete cycle, if it doesn't have as large of an acceleration, it's going to take more time, hence increasing the period. And then for the spring constant, if we increase the spring constant, we're going to decrease the period. Main thing for that again, larger spring constant means a larger force, which means a larger acceleration, which means a larger change in velocity. So with a large spring constant, this thing is going to pick up speed really quickly. It's going to be able to make a complete cycle much quicker. So if we increase the spring constant, we will decrease the period. What you may have noticed though is that the period has no dependence on amplitude. So no matter how far you stretch it from equilibrium, the period should be the same each time as long as m and k don't change. And the reason for that, we're going to give you the short explanation of it. So if you do have a smaller displacement, you are going to have a smaller restoring force. Now, if you have a much larger displacement, yes, you have a larger distance to cover, but that is going to be compensated by the fact that that larger distance is also going to give you a larger restoring force. So that's just kind of to give you a little bit more depth on that one. So let's look at some examples here. So we get a mass. It is 2.50 kilograms. It happens to be attached to a horizontal spring system and oscillates with an amplitude of 0.800 meters. Spring constant is 40 newtons per meter. Let's find the period. No unit conversions, so we know our oscillator, the period is going to be 2 pi square root m over k. No conversions, no rearrangement. This is a plug and chug. So this is a nice question. You don't have to do anything special with it. So we have that 2.50 kilograms. We're going to divide it by the spring constant, and we're going to square root it. So this amplitude of 0.800 meters, great, but it doesn't help us out. It's distracting information. They're trying to bait you into doing something you shouldn't. So let's calculate this. What we're going to get is we're going to get that the period is about 1.57 seconds. So for this oscillator to do a complete cycle, so to go to the one side, back to the starting side, it's going to take 1.57 seconds. Let's do one that's a little bit more involved. So we want to find the mass of a horizontal spring system if it oscillates with a period of 2 seconds and a spring constant of 20 newton per meter. Right. We have T equals 2 pi divided by the square root of m over k. What we're interested in is we're interested in the mass. What makes this a little bit more challenging? The mass is buried under a square root and there's all this other lovely stuff attached to it. How we approach this, there's a few different ways. So the first, probably most important thing is we want that square root gone. So we're going to square both sides. So what that means, I'm going to rewrite my equation here. So I got this m over k. So we're going to square both sides. The square applies to everything. So what we have here is we have t squared. So then we're going to have 2 squared, because that 2 is going to be squared, this pi is going to be squared, and then the square root of m over k, that is all going to be squared as well. So we're going to get t squared is equal to 4 pi squared, and then squaring that square root is just going to get rid of the square root, so then we have m over k. So I have t squared is equal to 4 pi squared m divided by k. My interest here is going to be the mass. So what we're going to do is we are going to get rid of this k first of all. Let's multiply both sides by k. So what I'm going to get is I'm going to get kt squared is equal to 4 pi squared m. Let me write that up here. just so we have it for reference. Well, I'd like the mass, so let's divide by this 4 pi squared. Let's divide by this 4 pi squared. So what we're going to find for this system is that the mass is equal to kT squared divided by 4 pi squared. The biggest mistake students will make in the calculator, again, we have more than one term in the denominator. In your calculator, make sure you put brackets around the 4 pi squared because we want to divide the top by this whole piece. So the last little bit here, we have a spring constant of 20 newtons per meter. We have a period of 2 seconds squared. We're going to divide that by 4 pi squared. So we get 20 times 4 divided by 4 pi squared. So what we're going to get is we're going to get about 2.0 kilograms. So this oscillator is going to have a mass of 2 kilograms. Not big, but it is what it is. So with these questions with the period and this relationship with the period, trying to find mass or the spring constant, they're a little bit more challenging because the rearrangement is not quite as simple as some of the other ones. When we have square roots and we got to deal with that, it makes things a bit more complicated. But the main thing to remember, if you're applying a power on a bunch of terms, that power applies to everything. So don't disappoint your Math 10C teacher and get that wrong. Right, let's look at the very last thing here. So we have a 0.150 kilogram mass, and it oscillates horizontally on a spring with a period of 0.50 seconds and an amplitude of 25 centimeters. So we want to find the spring constant, the maximum spring potential energy, and the maximum speed of the mass. All right, a very involved question. We can handle this. Now, I don't like my amplitude being in centimeters. We're going to put that in meters. This in kilograms is fine. This in seconds is fine. All right. We would like to first of all find the spring constant. So knowing the amplitude and the period and the mass, we know that T is going to be 2 pi square root m over k. We want to find k. This one is a little bit more involved. Now I'll show you a second way to rearrange this. We squared everything off the bat. The first thing we could actually do is we could divide by 2 pi on both sides, because then we kind of get the square root on its own. So we get this T over 2 pi is equal to square root m over k. Now what we're going to do is we're going to square both sides. So I square that, I square that. The square applies to everything. So I'm going to have T squared. 2 squared is going to give me 4. Pi squared is going to be pi squared. And then this square on the square root is going to get rid of that. So I got m over k. Now I'd like to solve for k. We have one fraction equals another fraction. I'm going to do what your math teachers hate. We're going to cross multiply. So I'm going to multiply this k with t squared. So that's going to give me kt squared. I'm going to multiply this 4 pi squared with m. So I'm going to get kt squared is equal to 4 pi squared m. My interest is our friend k. It's up in the numerator now, so we can divide both sides by t squared. So I'm going to get this k is equal to 4 pi squared m divided by t squared. So we have 4 pi squared. We have our mass of 0.150 kilos. We have that period of 0.50 seconds. Don't forget to square it. That's the big thing. So then lastly, let's calculate it. So we got 4 pi squared times 0.150 divided by 0.50 squared. This is going to give me about 23.687 newtons per meter. Now we want to write that with appropriate sig digs. We should have 2. So we're going to say that the spring constant's about 24 newtons per meter. Right, that takes care of the first part. Part B, we want to find the maximum spring potential energy, or the maximum elastic potential energy. So we know that potential energy for a spring is half kx squared. Since we'd like to find the maximum, we're going to have half k x max squared. All right, we just found the spring constant. We have been given, again, x max. This is our amplitude, which has been provided in the question. So we actually know everything for this. The only thing we want to watch for is for the spring constant. We want to use our unrounded value. We don't want to use 24. We want to use an unrounded value there. And of course we also want our amplitude to be in meters. So very important that this is the unrounded value. So I'm going to multiply that by 0.5, 2 squared. So what that's going to do is that's going to give me about 0.7402 joules, taking some extra sig digs. But again, if I want to actually apply my rules of sig digs for answering the question, we could say that the maximum potential energy, or the spring potential, this is about 0.74 joules. And the last part, we want to find the maximum speed. So we said to find maximum speed, we said we know that EK max is equal to EP max. Now, we know EK max is going to be half mv max squared. Now, you can write EP max is equal to half kx squared, but there's no point in doing that. We already calculated EP max. We've already done that, so why would we repeat that calculation again? So we're just going to leave it as EP max. So we would like to solve for V, so we need to get rid of this half. We're going to multiply both sides by 2. So I'm going to get mv max squared is equal to twice this maximum potential energy. And then we're going to divide both sides by the mass here. So I'm going to get V max squared is 2 EP max divided by m. Then the last step, let's square root both sides. So then I'm going to get V max is equal to the square root of 2 EP max over m. Last thing, let's plug in what we know. Again, for that maximum potential energy, we don't want to use 0.74 joules. We want to use an unrounded value. So we want to take as many digits from the calculator as possible. So again, unrounded. And then the last thing we'll do is we've got to square root this whole thing. Don't forget your square root. That's always the killer for these type of questions. So the last thing, we are going to get roughly about 3.1 meters per second. So for this oscillator, we're going to say that its max speed is about 3.1 meters per second. This type of question here, this is probably the most challenging type of oscillator question you get, just because you have to link so many ideas together. But as long as you remember the fundamentals, and especially for that max speed, that EK max equals EP max, we can't throw anything too difficult at you. You'll be prepared for every single question.